Hello and welcome to Some Assembly Required. In this video we will finally be implementing an opcode. The video itself turned out a little too long, about 1 hour. So I split it up into 3 parts. The first part, that's the part you're watching right now, is all about preparing the implementation. So we collect the data we need, we match it up against the actual 6502, and we create the test bench test plan. That's this video. The next video will be about implementing the actual opcode. And the third video, which hopefully will be the last one, will be about implementing the flags. Now, you'd expect the flags not to require a whole video. I know I did. But turns out things didn't go exactly according to plan, and there was some more tinkering to do than expected. So there you have it. I hope you enjoy. The first thing we need to do is choose which opcode we want to implement. As usual, we're going to be using the 6502 datasheet from Western Design Center. All the opcodes are listed in page 22, and I've marked in green all the opcodes that I've already implemented. So all those not marked are the ones that are good candidates for us to implement. Since I want an interesting opcode to implement, let's go with rotate left. This is rotate left in absolute addressing mode. The opcode is 2E. The first thing we want to do is check out how this opcode is supposed to behave. Opcode behavior in the 6502 is pretty much determined by the addressing mode. So if we check the addressing modes, we see the absolute addressing mode takes 4 cycles to execute, and the address itself takes 3 bytes, which makes sense because we need 1 byte for the opcode and 2 bytes for the address from which we're reading or writing. You will also notice footnote number 3, which says that for read, modify, write, add 2 cycles. We'll get to this in a moment. Before that, let's try and understand what absolute address means. And for that, we can turn to page 15, where absolute address says we have the opcode at offset 0, and then the address low at opcode at offset 1, and address high in offset 2. And the operand address is the address low and the address high. So essentially just read 2 bytes from memory, compose them into a 16-bit absolute address, and then use that address for the operand. What's important to understand for our implementation is that the different addressing modes differ in the way they calculate where the operand is, but the actual operation is the same for all operand types. And this is important because in my implementation, the operand addressing is done in a generic way for all opcodes, so we're not going to be implementing it now. We've already have it implemented, and I'll show you the interface in a second. Page 27 contains all the opcodes in alphabetic order. We're looking for rotate left, so that's this opcode. This table explains what the opcode should do. So it takes bits 0 through 7 of the operand. It shifts them all left, with bit 7 going into the carry, and the carry going into bit 0. So that's the rotate operation. You will also notice that we need to update the negative, 0, and obviously carry flag. I say obviously because it's spelled right here how the carry flag needs to be updated. As usual, the negative flag is set if bit 7 is set, and the 0 flag is set if none of the bits are set. What's interesting about this command is that it doesn't affect any of the CPU registers, except the flags, of course. It takes the value from memory, so it calculates an absolute address and uses that as the operand, reads it, rotates the value, and writes it back to the same address directly. Such a command is called read, modify, write. And we've seen that mentioned in this video before. Going back to addressing mode, remember comment number 3. Read, modify, write, add 2 cycles. To understand why those 2 extra cycles are needed, let's go back to our Visual 6502 simulation. If this is your first time seeing this site is called Visual 6502, and it contains a transistor level simulation written in JavaScript of all languages of the 6502, the original MOS 6502. And it provides a high fidelity cycle-by-cycle simulation of the CPU's operation. So to see how it works, let's put in the opcode here, that's 2E, And let's say we write into 50. So that's 5000. It scrolls away. And let's put here 00 just so we can see the break instruction and know we're done. Of course, here let's put some value. Let's say 3F. And so we can see it working. Press the up button. The bus is updated. We can see that we're reading from address 000. We're reading the value 2E. And it decodes for us as rotate left absolute. RW1 means this is a read. Everything's fine. So that's the low phase of the clock. The high phase of the clock looks pretty much the same. Cycle number 1, we're reading the first part of the operand of the address. So that's the 50 and then the 00. So these 3 cycles are the 3 cycles of decoding the complete operation. The timing table also leaves us 1 cycle to perform the actual operation. That's the reason it says 4 here. So 3 cycles to decode the whole thing, and then 1 cycle to actually do something. In our case, we're reading from the address 50. Of course, reading is not enough. We need to actually write something back. So cycle number 4 again accesses address 50 and it writes 3F, which is really strange because that's not the correct value. But then cycle 5 still writes to address 50, but writes the value 7E, which actually is the correct value. Now, this might seem a bit strange, the 2 write cycles. And you know what? It is strange. I'll get to that in a second. But before that, what you'll notice is that we actually took 6 cycles to perform the operation and not 4 like the table said. At least the next instruction is a new instruction with a break. So 6 cycles is how long it took, which is what this comment is all about. It says, if your operation is a read, modify, write, such as rotate left on absolute address, add 2 cycles to the execution time. So 6 cycles altogether. The reason we need those 2 extra cycles is on cycle number 3, that's the 4th cycle, we're reading the value in which we operate. And it's only available at the very end of the cycle. And if you need to understand why, check out the previous video which explains that. That means we have 1 cycle in which we need to write back the result, and 1 cycle in which we need to actually calculate the result. So those are the 2 extra cycles. Read, modify, write. I said the extra write seems strange, and turns out it is. Page 30 of the datasheet contains differences between the original MOS 6502 and the Western Design Center 65C02. And we see here that read, modify, write instruction at effective address on the MOS did 1 read and 2 write cycles, and on the W65C02 does 2 reads and 1 write cycle, which makes more sense. So when we're implementing our own instruction, we need to select which of the 2 we're going to do. And for the time being, we're going to do this, and we will circle back to it later. Right, so we have our marching orders. Let's get going. The first thing we need to do has nothing at all to do with implementing the opcode, in a way. The first thing we need to do is set up the simulation. Pretty much any FPGA and even any hardware development platform has a simulation mode. In the simulation mode, we can take the module we're building, hook it up to a simulated circuit, and see how it behaves. And in our case, our circuit feeds it a clock and feeds the memory certain addresses. And we can see the values propagate throughout the different CPU functions. This is called the test bench. Our test bench has 2 files defining it. The first file is the memory image. our memory is 64 kilobytes or 65,536 bytes. And for some of them, we define in this file what their initial value is going to be. Of course, the CPU is free to write to pretty much any of them. So if we want to add a new opcode and we want the test bench to test it, the first thing we need to do is find out at what address does the test finish. In our case, that's 839. Go to the memory at that address, 839, and end our command. 2E, we need to read from somewhere, right? So we need 3 bytes at this point. We need 2 bytes, that's 16-bit, of the address in which our operand will reside, and we need the initial value to place there. And I found the best way to do that is to generate 3 random bytes. We're going to read from dev random with a block size of 1. We're going to read 3 bytes, and we're going to pipe them through hex dump. So there you have it. We're going to write 94 to the address C7F4. So C7F4 gets 94. Of course, once we got those, we know how to encode them. So least significant byte of address first, that will be F4C7. Actually, before I do that, I want to make sure the carry is in a known state. So I want 0839 to actually be clear carry, which means that this will be 083A. Clear carry is 18. And of course, we want to update here the address from which we're writing to this value. Personally, after each test, I like to place a no operation just to pad the differences. So that would be a no operation, and it's at address 3A, 3B, 3C, 3D. And that's actually enough for us to be able to start testing how this works. If we go back to the simulation and ask for reload, we can run the simulation. It finishes at 0839. If I zoom in a little, I can see that it's reading the value 18. Since we know the carry flag is flag 0, we can actually rename this, but for some reason it doesn't stick. While we're at it, let's rename the others. 0 and that's negative with an N, of course. So we expect this command to clear the carry. Let's see if it does. 35 microseconds each time we click this. This skips exactly half a cycle. Sorry, 35 nanoseconds. So reset, run until it's finished, and then we can skip half a cycle at a time. So that's the first cycle of the clear carry. Sorry, that's the last cycle of the no operation. This is the first cycle of the clear carry. And this is the second cycle of the clear carry. And we see that the carry is cleared. Great. Next, there's the rotate left operation, which of course we haven't implemented yet. Right now, the CPU is configured to treat unknown opcodes as no operation. So this will take 2 cycles. Let's just skip to the end here. And it advances the program counter. and the address bus. And then it brings the sync line high, which means that as far as it's concerned, it just started a new instruction, which of course is the wrong handling for this opcode, but we haven't implemented it yet. And at this point, we can start implementing, and we will see in the simulation how it works. But that's not good enough. I want automatic verification that it works correctly. And in order to do that, we need one more file. The file is called expected results, but I think a better name for it would be test plan. And if we skip to the end of the file, we see an end marker. This end marker is the reason the simulation stops. When our simulation sees the end marker in the file, it just stops the simulation, which is why we stopped right at the new instructions we added to the memory. But the other lines also tell the simulation what to expect. And we have an explanation. We see that I think the interesting ones for us are, if it says 0, this is an opcode with an implied operand, which means that we do not verify the memory access as it does. If we say 1, it means it's an opcode that reads from memory. And if it says 2, it's an opcode that writes to memory. And the rest of the fields, the second field is the number of cycles this opcode is expected to take. The next field is the opcode itself, the opcode number, the address from which the opcode is fetched, and then the last cycle of the opcode, what value it should read or write, depending on what type it is, and where it should read or write from. So, going back to the end of the file, we want to add an implied addressing mode that takes 2 cycles. The opcode is 18, which is clear carry. It's going to be read from 0839. Since this is an implied, we do not tell it what value it needs to do on the last cycle. It doesn't matter. And the last access will be to the next address where the next instruction is going to be read, because the instruction takes 2 cycles and it doesn't do anything interesting with the memory on its second cycle. Let's also say that this is the ROL test. The second instruction is doing a write. It needs to take 6 cycles. The opcode is 2E. And the last access is going to be to address C7F4. Sorry, it's going to be read from 083A. And the last access is going to be to address C7F4. And it's going to write, well, we read 9.4. Effectively, we'll be multiplying by 2. So we need to write back 2.8. And we finish it off with another no operation, which is an implied operand, 2 cycles. The opcode is EA. It is read from 083D. We're not interested in what it does. And the last access will be to 083E. So that's our test plan. That's what we expect the program to do. Unsurprisingly, that's not what it will do, simply because we haven't implemented the opcode yet. So we reset, we run, and we see an assert failure. And it says that after writing 148 events running correctly, we have a last access. Oh, yeah, that's not the correct error at all. Now we can run the simulation. And we get an assert failure. It says opcode shorter than expected. Let's understand why. There is exactly 30 lines difference between the number of events and the line number. So 150 is 180. That's our rotate left. And we said that it needs to take 6 cycles. However, if we look at the simulation, we see that it only took 2 cycles until the sync went high again, which makes sense because our CPU thinks that's an operation. So the simulation stopped with an error, which is great. It means that now we can automatically test whether we've implemented correctly the opcode. That is a huge thing. It means that as we continue to implement opcodes in the CPU, all we have to do in order to make sure we haven't broke the rotate left opcode is run the simulation. It will automatically make sure everything's in order. With that out of the way, we can finally start implementing the actual opcode. So that's it for the first video. If you've enjoyed it, please hit the like button. It helps with spreading the word, so to speak. The next videos will be available shortly, I hope. Thank you for watching.